Good morning. It is good to see you all here. We are going to talk about something today that you think you know very well. We are going to talk about the ground under your feet. We are going to talk about why you don't float away into the ceiling. We are going to talk about gravity. Now you might say, I know what gravity is. It is the thing that makes apples fall on heads. And you would be right, but you would also be wrong. You see, what we usually call understanding in physics is often just a fancy way of saying we have a name for something. We name it gravity, and we feel better. We feel like we have solved the puzzle. But have we? If I drop a piece of chalk, it goes down. It picks up speed as it goes. If I throw it up, it slows down, stops for a tiny moment, and then comes back. We see this every day. It is the most common thing in our lives. Because it is so common, we stop asking questions about it. We take it for granted. But in science, the things you take for granted are the most dangerous things. They are the places where nature is hiding her best secrets. I want you to throw away what you think you know for a moment. I want you to look at the world like a child who has never seen a ball fall before. Why does it move? Does the earth pull it? Does the space push it? Is it magic? For a long time, people thought it was just the nature of things. Heavy things belong down. Light things, like fire, belong up. It was a nice idea. It made us feel like everything had a place. But it didn't tell us how things moved. It didn't give us a number. You couldn't calculate anything with heavy things belong down. Then came a man named Isaac Newton. Now Newton was a clever fellow. He didn't just want to say things fall. He wanted to say exactly how fast they fall. He wanted to predict where a cannonball would land. He wanted to know why the moon goes around the earth. He had a hunch that the force pulling the apple to the ground was the same force holding the moon in the sky. This was a huge leap. It sounds obvious to us now, but back then, it was crazy. The apple is here. The moon is way up there. Why would they follow the same rule? The earth is dirty and messy. The heavens were supposed to be perfect and divine. Newton said, no, the rules here are the rules there. This is the first great unification in physics. But Newton had a problem. The math of his day wasn't good enough. If you want to track a falling apple, you have a problem. The speed of the apple is changing every single instant. It is faster now than it was a second ago. It is faster now than it was a half second ago. How do you do math on something that never stays the same? If you drive a car and you go 60 miles an hour for 1 hour, you go 60 miles. That is easy math. But a falling apple is like a car that is constantly pressing the gas pedal. The speed is changing, the position is changing, everything is fluid. So Newton had to invent a new tool. He invented a way of thinking about tiny, tiny slices of time. This is what we call calculus. Now don't let the name scare you. People try to make calculus sound like a dark art. It isn't. It is just a way of looking at the speedometer. Think about your car. You look at the speedometer and it says 60. What does that mean? It means if you kept going exactly this way for an hour, you would go 60 miles. But you might hit the brakes in 2 seconds, so that 60 is a measure of right now, an instant. Calculus is the trick of taking a curved line, like the path of a ball thrown in the air, and chopping it up into tiny little straight lines. If you chop it up enough, if you make the pieces small enough, the curve disappears. You can treat it like a straight line. Then you do your simple math. Then you put all the tiny pieces back together. That is all it is. It is the science of chopping things up and gluing them back together. Newton used this to write down his famous laws. He gave us an equation. It was beautiful. It told us that the force of gravity gets weaker as you move away. If you go twice as far, gravity is 4 times weaker. If you go 3 times as far, it is 9 times weaker. It worked perfectly. It explained the tides. It explained the planets. We could predict where Mars would be in 100 years. We felt like masters of the universe. We thought we had figured it all out, but there was a ghost in the machine. There was something about Newton's theory that didn't smell right. Even Newton knew it. He didn't like to talk about it, but it bothered him deeply. The problem was this: how does the Earth know the sun is there? Look at the sun. It is 93 million miles away. That is a long way. There is nothing between us and the sun but empty space. A vacuum. Nothing. So according to Newton, the sun reaches out across 93 million miles of nothingness and grabs the Earth instantly. If the sun disappeared right now, Newton's math says the Earth would instantly fly off in a straight line. The Earth would know immediately that the sun was gone. How? Does the sun send a messenger? Does it have a long invisible rope? If I want to pull you, I have to touch you, or I have to use a rope, or I have to throw something at you. I can't just wiggle my finger here and make you move over there without touching the space in between. This is called action at a distance, and strictly speaking it is impossible. It doesn't make sense. It is like voodoo magic. You stick a pin in a doll here and someone hurts over there. Science doesn't like voodoo. Science likes mechanisms. We like to see the gears turning. Newton wrote a letter to a friend about this. He basically said, if you think gravity can act across empty space without any medium, you are a fool. I am paraphrasing, but that was the spirit of it. He knew his formula worked, but he knew his theory was missing the why. He famously said, I frame no hypothesis. He meant, I know the math works, don't ask me how it happens. So for 200 years we used a formula we didn't really understand. We calculated orbits, we built bridges, we felt smart, but we were ignoring the giant invisible elephant in the room. We were ignoring the fact that our best theory relied on magic. Then we started to learn about electricity. This gave us a clue. Imagine you have a magnet and a pile of iron filings, little metal shavings. You put the magnet down, the filings jump. They form a pattern, lines, loops. They don't just sit there. They show you something invisible. They show you that the space around the magnet is different. The magnet has changed the air around it. It has created a field. This was a huge idea. The magnet doesn't touch the iron directly. The magnet changes the space and the iron feels the space. It is like a bucket brigade. The magnet tells the point next to it, hey, I'm here. That point tells the next point. And so on until the news reaches the iron. This solved the action at a distance problem. There is no magic jump. There is a field filling the space. So physicists thought, aha, gravity must be a field too. The Earth creates a gravity field. The moon sits in that field and feels a tug. It sounded good. It made sense. But then came a man named Albert Einstein, and he turned the whole table over. Einstein looked at gravity and said, you are all thinking about this the wrong way. You are thinking of gravity as a force. You think it is like a muscle pulling on a rope. You think it is like a magnet pulling on iron. It is neither. Einstein had a very simple, very strange, he called it the happiest thought of his life. Imagine a man falling off a roof. I know it's not a happy image, but stay with me. While the man is falling, does he feel gravity? If he lets go of his keys, do they fall to his feet? No, they fall with him. If he tries to pour a cup of water, the water doesn't pour down. It hovers right in front of the cup. Everything falls together. To the man falling, gravity has vanished. He feels weightless. He feels exactly like an astronaut floating in deep space. Einstein said, this is not an accident. This is a rule. If you can cancel out gravity just by falling, maybe gravity isn't a force at all. Maybe gravity is just motion. This led him to an idea that is so strange, so beautiful. It is hard to believe it is true, but it is. Einstein said, gravity is not a pole. Gravity is the shape of the universe. Let's try to picture this. I want you to imagine a trampoline. You know, the kind kids jump on, a rubber sheet pulled tight. If you roll a marble across the empty trampoline, what does it do? It goes in a straight line. Easy. Now take a heavy bowling ball and place it right in the middle of the trampoline. The rubber sinks down, it curves. It makes a valley. Now roll the marble again. What happens? The marble tries to go straight, but the surface it is rolling on is curved. So the path of the marble curve, it circles around the bowling ball. It might even spiral in and hit it. If you looked at this from above, and you couldn't see the curve, you would say, look, the bowling ball is pulling the marble. But there is no pull, there is no rope, there is no magnet. The bowling ball just bent the sheet, and the marble is following the curve. Einstein said, this is what is happening in the real world. But instead of a rubber sheet, the heavy object, like the sun, then space-time. Now space-time is a fancy word. Don't let it scare you. It just means the stage where everything happens. The 3 dimensions of space, up, down, left, right, forward, back, plus the dimension of time. Wait, time? Yes, time too. The sun bends time. Clocks run slower near heavy things. Your feet are slightly younger than your head because they are closer to the earth. It's a tiny amount, but we can measure it. It's real. So according to Einstein, the earth isn't being pulled by the sun. The earth is trying to go in a straight line. It is coasting, but the space around the sun is curved like a valley. So the straightest possible line the earth
can take is a circle. This is a radical change. Newton said, gravity is a force that acts on things. Einstein said, gravity is the shape of the container that things are in. To prove this, Einstein had to use some very difficult math, much harder than Newton's calculus. He had to use the geometry of curved surfaces. Think about an ant walking on an orange. The ant thinks he is walking in a straight line, but if he walks long enough, he comes back to where he started. His world is curved. The rules of flat paper don't work on an orange. The angles of a triangle don't add up to 180 degrees on an orange. Einstein had to write equations that describe how mass, the bowling ball, tells space how to curve, and then how that curved space tells the marble how to move. It is a dance. Matter tells space how to curve. Space tells matter how to move. This theory is called general relativity, and when Einstein released it, people were shocked. It was elegant. It got rid of the spooky action at a distance. There was no magic rope. The sun bends the space right next to it. That bent space bends the space next to it, and so on, until the bend reaches the earth. It takes time for the bend to travel. It moves at the speed of light. If the sun vanished now, the earth would keep orbiting for 8 minutes. We wouldn't know the sun was gone until the unbending of space reached us. The ripple had to travel. This solved Newton's headache. It made physical sense, and it made predictions that were different from Newton. One of the most famous tests happened during a solar eclipse. If Einstein was right, light should fall too. Light has no mass, but it travels through space. If space is bent, the path of light should bend. Imagine a star that is essentially behind the sun. You shouldn't be able to see it. But Einstein said the light from that star would pass the sun, get caught in the dip in the trampoline, curve around and come to Earth. We would see the star, but it would look like it was in the wrong place. In 1919, astronomers went out during an eclipse to check. They took photos, they measured the position of the stars, and guess what? Einstein was right. The light bent. The space was curved. The headlines the next day said, "Lights all askew in the heavens." It made Einstein the most famous scientist in the world. So are we done? Is the mystery solved? Is gravity just geometry? It feels like the answer should be yes. It is such a clean picture. It explains black holes, places where the trampoline rips, because the bowling ball is too heavy. It explains the Big Bang. It explains the GPS in your phone. Yes, without correcting for curved time, your GPS would drift by miles every day. But there is a catch. There is always a catch. Nature is not that easy to please. You see, while Einstein was looking at the stars and the big heavy things, other physicists were looking at the tiny things, atoms, electrons, and they found a world that was completely different. Einstein's world is smooth. The rubber sheet is smooth. You can slide down it gently. You can measure the curve anywhere. It is predictable. The world of the atom is not smooth. It is jumpy. It is pixelated. Energy doesn't flow like water. It comes in little packets. We call them quanta. In the quantum world, things don't have exact positions. They are fuzzy. A particle isn't here or there. It is kind of in both places at once, until you look at it. It is a world of probability, not certainty. And here is the terrible secret, the thing that keeps physicists up at night. Einstein's smooth, gravity, and this jittery quantum world do not get along. They hate each other. If you try to take Einstein's beautiful curved space and zoom in, and zoom in, and zoom in, down to the size of an atom, the math breaks. It falls apart. Einstein assumes space is flat and smooth. If you look close enough, quantum mechanics says if you look close enough, space is a violent, boiling foam of energy. It is chaotic. You cannot have a smooth, rubber sheet that is also made of boiling foam. This is the crisis of modern physics. We have two rule books, one for the big stuff, gravity, one for the small stuff, quantum mechanics. Both rule books work perfectly in their own territory, but they contradict each other. It is like having a map of the city that says north is up and a map of the country that says north is down. They can't both be right everywhere. So we know that Einstein's story, as beautiful as it is, cannot be the whole truth. It is an approximation. It is a very, very good lie, but it is still a lie. There must be something deeper. There must be a way to describe gravity that explains the curve and the jitters. We have been looking for this for 80 years. We call it quantum gravity. We haven't found it yet. This brings us back to the chalk falling. What is actually happening? Is it following a curve in space? Yes, but what is space made of? Is space made of tiny particles? Is space made of loops? Is space an illusion? Some new theories suggest that gravity might not even be a fundamental force. It might be a side effect. Think about heat. What is heat? Is heat a fluid? No. Heat is just the jittering of atoms. If you have enough atoms moving fast, you feel heat. Heat is an emergent property. It comes from the chaos of the small stuff. Maybe gravity is maybe gravity is what happens when you have a lot of quantum stuff interacting. Maybe curved space is just what it looks like from far away, like how a newspaper photo looks smooth from a distance, but is made of dots when you get close. If that is true, then gravity is truly an illusion. It is a shadow of something else. We are still trying to figure this out. We are building giant machines to smash particles together. We are looking at black holes because that is where the two worlds meet. A lot of mass, gravity squeezed into a tiny space. Quantum. Black holes are the keys to the kingdom. If we can understand what happens at the very center of a black hole, we will know the truth about gravity. But for now we are stuck with two beautiful theories that don't talk to each other. And that is the beauty of it. If we knew the answer, science would be dead. The fact that we don't know, that is what gets us out of bed in the morning. So the next time you drop your keys, don't just think gravity. Think about the invisible curve. Think about the bowling ball on the trampoline. And think about the tiny jittery mystery hiding inside that smooth curve. The world is not what it seems. It is far more interesting. And we have only just scratched the surface. I hope that gives you a sense of the problem. We start with a stone falling, and we end up questioning the nature of space and time itself. That is the fun of physics. You pull on a loose thread, and the whole sweater unravels. Now I want to take a step back and look at the tools we use to get here. I mentioned calculus. I mentioned geometry. These are just languages. Nature speaks in mathematics. We don't know why. It is a mystery. Why should the world follow rules that we can write down on paper? It is a miracle, really. The fact that we can predict an eclipse to the second, it tells us there is order. But the fact that we can't merge gravity and quantum mechanics, that tells us the order is more complex than our minds can currently grasp. We are like people watching a chess game. We don't know the rules. We watch the pieces move. We see that the bishop stays on the same color. We write that down. Law of bishops. Always stay on color. Then we see a castle move straight. We write that down. But then suddenly, a pawn becomes a queen, and we are confused. We didn't see that coming. Our rulebook was incomplete. Physics is the process of watching the game and trying to guess the rules. Newton guessed some good rules. Einstein guessed better ones. But we are still waiting to see the full rulebook. And that, my friends, is why gravity is not what you think. It is not a settled fact. It is an open door, and it is inviting us to walk through. So we have a problem, a big one. We have two beautiful maps of the world. One map, Einstein's map, tells us about the mountains and the valleys of space. It is smooth, it is elegant, it handles the big heavy things, like stars and galaxies. The other map, the quantum map, tells us about the dust and the sand. It handles the tiny things like atoms and electrons. The problem is, these two maps don't fit together. If you try to tape them together at the edges, the lines don't match. In fact, the paper catches fire. Let's dig a little deeper into why this happens. To understand the conflict, we have to look at how the quantum world thinks about force. Remember how we talked about Newton? He thought gravity was a rope. Then Einstein came along and said, no, there is no rope. The space is just bent. Well, the quantum physicists, the people studying the very small, looked at electricity and said, we don't like bent space. That's too complicated for us. We like particles. We like throwing things. Imagine two ice skaters standing on a frozen pond. They are standing still, facing each other. Now one of them throws a heavy medicine ball to the other. What happens? The skater who throws the ball slides backward. That is the recoil. The skater who catches the ball slides backward. 2. The force of the throw pushed them apart. To a person watching from a helicopter, looking straight down. Maybe they can't see the ball. The ball is too small, or moving too fast. What do they see? They just see two skaters mysteriously moving away from each other. They would say, look, there is a repulsive force between them. But we know it wasn't a mysterious force. It was the exchange of an object. In the quantum world, this is how forces work. Electricity isn't just a fluid. When two electrons push each other away, they are playing catch. They are throwing invisible particles back and forth. We call these messenger particles photons. Yes, the same photons that make up the light coming from your lamp. Light is just the messenger particle of the electromagnetic force. It is the medicine ball. This idea that forces are actually made of particles is the heart of what we call the Standard Model. It works beautifully. It is perhaps the most successful theory humans have ever invented. We can use it to calculate the magnetic strength of an electron to 10 decimal places, and when we measure it in the lab, the numbers match exactly. It is like measuring the distance from New York to Los Angeles and being right within the width of a human hair. That is how good this theory is. So naturally, physicists got cocky. They said this particle exchange idea is great. Let's use it for gravity. If electricity is carried by a photon, then gravity must be carried by a graviton. It makes sense, right? If the Earth pulls the moon, it must be because the Earth and the moon are throwing billions of tiny invisible gravitons back and forth, a blizzard of little particles tying the universe together. So we took our notebooks and we started to do the math. We tried to write down the rules for how these gravitons would move, and that is when the machine exploded. To understand why it exploded, I have to tell you a little secret about how particles move, and this is going to sound like I am making it up. I promise you, I am. Nature is just this strange. When you throw a baseball from home plate to first base, it takes one path. It goes in an arc, a nice predictable curve. But when an electron moves from point A to point B, it doesn't just take one path. It takes every path. I mean literally every path. It takes the straight path. It takes a curved path. It goes to the left. It goes to the right. It goes up to the ceiling, does a loop-de-loop, and comes back down. It goes to the moon, circles a crater, and comes back. It goes to the edge of the universe and returns. The electron sniffs out every possible route in the entire universe simultaneously. Now you are thinking, that is ridiculous. A particle can't be in a million places at once. But in quantum mechanics, it can. The particle isn't a hard little marble. It is a wave of probability. It explores all options. When we do the math to predict where the particle will end up, we have to add up all these paths. We call this a sum over histories. We sum up the history of the particle going left, the history of it going right, the history of it going to Mars. Most of the crazy paths cancel each other out. The path going way left cancels the path going way right. The only paths that survive the math are the ones right in the middle, the ones that look like the straight line we expect. That is why in the big world, baseballs don't fly to the moon on their way to first base. The weirdness cancels out. But in the tiny world, the weirdness matters. You have to account for it. So we tried to do this sum of all paths for the gravity. We said, okay, let's imagine a graviton moving from the Earth to the moon. Let's add up all the paths it could take. But here is the catch. Gravity is special. Photons, light particles, do not have electric charge. They carry the force, but they don't feel the force. Two flashlights beams pass right through each other. They don't crash. But gravity is different. Gravity comes from energy. Anything that has energy has gravity, and gravitons have energy. Do you see the problem? If a graviton has energy, then it has its own little bit of gravity. It creates its own little gravitational field. So the graviton creates gravity. That new gravity creates more gravitons. Those new gravitons have energy, so they create more gravity. It is a feedback loop. It is like holding a microphone next to a speaker. You get a scream. The noise feeds on itself and gets louder and louder until it blows out the speaker. When we try to calculate the path of a graviton, the math doesn't just give us a big number. It gives us infinity. We ask what is the probability of this happening, and the equation says infinity %. We ask how strong is the force, and the equation says infinite pounds. Infinity is not a number in physics. Infinity means you are wrong. It means your theory has broken down. You cannot have infinite energy in a finite space. We tried everything to fix. We tried to use the tricks that worked for electricity. In electricity, we sometimes get infinities too, but we know how to sweep them under the rug. We call it renormalization. It's a fancy word for a shell game. We hide the infinity in a box and say let's just measure what we see in the lab and use that number instead. It feels like cheating, but it works. But with gravity, the shell game fails. The infinities are too big. They are too many. You sweep one under the rug, and 10 more pop up behind the sofa. The harder you try to zoom in on the graviton, the worse the math gets. The foam of space-time becomes so violent, so twisted, that concepts like left and right, or before and after, stop making sense. This is the great disaster. Einstein's smooth geometry refuses to be chopped up into quantum dots, and the quantum dots refuse to be smoothed out into geometry. So why haven't you noticed this? Why doesn't the universe fall apart? Because usually, you don't need both maps at the same time. If you are an astronomer looking at a black hole from a distance, you use Einstein, you ignore the atoms. If you are a chemist looking at a molecule, you use quantum mechanics, you ignore gravity, because gravity is so weak compared to electricity. Think about it. A tiny fridge magnet can pick up a paper clip against the pull of the entire Earth. That's how weak gravity is. So usually, we can stay in our separate corner. The general relativists stay in the astronomy department, and the quantum mechanics stay in the particle physics department, and they don't talk to each other. But there are places where you can't ignore it. There are places where you need both. These are the places where the monsters. I am talking about the center of a black hole. What is a black hole? It is a tremendous amount of stuff crushed into a tiny space. Because it is heavy, you need gravity. Einstein. Because it is tiny, you need particle physics. Quantum. You are forced to overlay the two maps. And when you do, the paradoxes scream at you. According to Einstein, the center of a black hole is a singularity, a point of infinite density, a bottomless pit in the rubber sheet. But quantum mechanics says, you can't have a point. Points don't exist. Everything is away. Everything is fuzzy. You can't squeeze a particle into zero space. It will fight back. It will jitter. So what really happens at the center of a black hole? Does space end? Does time stop? Does it bounce and create a new universe? We don't. We literally do not have the language to describe it. Our math gives us gibberish. And it's not just black holes. It's us, it's our history. Rewind the clock. Go back 13 billion years. The Big Bang. At the very beginning, the entire universe, all the stars, all the galaxies, all the light, was squashed into a space smaller than an atom. That is the ultimate black hole environment. Heavy and tiny. To understand where we came from, to understand the moment of creation, we need a theory of quantum gravity. Without it, we are blind. We can trace the history of the universe back to a fraction of a second after the beginning, but we can't get to the starting line. A curtain fall. This is why physicists are so obsessed with this. It is not just about tidying up the equations. It is about understanding our origins. So what do? We have been stuck here for decades, but we have some ideas, some wild ideas. One idea is called string theory. You might have heard of it on TV. String theory says, the problem is that you are thinking of particles as dots. Stop it. If an electron is a dot, a zero-dimensional point, then you can get infinitely close to it. And that is where the math blows. So string theory says, imagine the electron is not a dot. Imagine it is a tiny, tiny loop of string, like a rubber band. If it is a loop, it has a size. You can't get infinitely close to it, because it is not a point. It spreads the force out just enough to stop the infinity. It calms the math down. And the beautiful thing is, this string can vibrate. If you pluck a guitar string, you can make an A note. If you put your finger on it and pluck it again, you get a C note. Different vibrations, different notes. String theory says, particles are just notes played on these tiny strings. Vibrate the string one way, it looks like an electron. Vibrate it another way, it looks like a quark.
Vibrate it a third way, and it looks like a graviton. It is a lovely idea. It unifies everything. It turns the universe into a symphony. Gravity isn't an outsider anymore. It is just another note on the violin. And there is always a but to make the math work. String theory needs room to vibrate. The strings need more than 3 dimensions. We see left, right, up, down, forward, back. 3 dimensions plus time. That makes 4. String theory says, no, that's not enough. I need 10 dimensions, or 11. Where are the other 6 dimensions? The theory says they are curled up. They are tiny. Imagine looking at a garden hose from far away. It looks like a line, a one-dimensional string. But if you walk up close to it, you see it is a tube. It has a second dimension, the circle around the tube. An ant can walk along the hose, or it can walk around the hose. String theories say the extra 6 dimensions are like the circle on the hose. They are curled up so tight, smaller than an atom, that we can't see them, but the strings can feel them. The strings vibrate into these hidden dimensions. Is this true? Is our universe actually an 11-dimensional construct? It sounds like science fiction, and right now it kind of is. We have never seen a string. We have never seen an extra dimension. We have no experimental proof. Some people say string theory is just fancy math, not physics. They might be right, but it is the best hint we have right now. There are other ideas too. Loop quantum gravity says space itself is made of little distinct chunks, like pixels on a screen. You can't divide space forever. Eventually you hit a grain of space. That would solve the infinity problem too, because you can't have a singularity if space has a minimum size. So where does this leave us? We started this journey asking why an apple falls. We found out it's because space is curved. Then we looked closer and found the curve is made of jittery uncertainty. We tried to combine them and broke mathematics. Now we are talking about 11-dimensional vibrating rubber bands. It is a mess, but it is a glorious mess. It tells us that gravity as we experience it, the solid, reliable pull of the Earth, is likely an illusion. It is a simplified macroscopic effect of something much deeper, much stranger. Just like the temperature of the air is just the average speed of billions of atoms, the curvature of space is probably just the average behavior of something else. Strings, loops, information. We are like the early explorers staring at the ocean. We have mapped the coast, Newton. We have sailed to the islands, Einstein. But the deep trench, the bottom of the abyss, we haven't been there yet. And this is important to remember. Science is not about certainty. It is about doubt. If a scientist tells you this is exactly how it is and there is no other way, they are not doing good science. We must always leave the door open for the next Einstein. Maybe the next Einstein is sitting in a classroom right now. Maybe they are watching a video on the internet. Maybe they will look at our impossible problem and say, you are all looking at it upside down. Maybe gravity isn't a force or a geometry. Maybe it's something we haven't even invented a word for yet. For now, the best we can do is appreciate the mystery. Next time you look at the stars, remember that the light hitting your eye is bending around the sun, riding the curves of space-time. And remember that inside every one of those stars, atoms are dancing a quantum dance that defies common sense. The universe is a master illusion. It shows us a world that looks solid, flat, and predictable. But behind the curtain, it is a kaleidoscope of vibrating strings, bent time, and infinite possibilities. Gravity is the lie that holds it all together. And frankly, I think the lie is beautiful. But the truth, when we finally find it, will be even better. Thank you for listening. Keep asking questions.